Today I'm going to be reading this book to you, and the chapter is chapter number 1, Kinematics Describing Motion. This is the chapter we are going to be reading today, chapter number 1, Kinematics Describing Motion. Learning Outcomes. You should be able to define displacement, speed, and velocity, draw and interpret displacement time graph, describe laboratory methods for determining speed, use vector addition to add two or more vectors. Describing motion. Our eyes are good at detecting movement. We notice even quite small movements out of the corners of our eyes. It is important for us to be able to judge movement. Think about crossing the road, cycling or driving, or catching a ball. Figure 1.1 shows a way in which movement can be recorded on a photograph. This is a stroboscopic photograph of a boy juggling 3 balls. As he juggles, a bright lamp flashes several times a second so that the camera records the positions of the balls at equal intervals of time. If we knew the time between flashes, we could measure the photograph and calculate the speed of a ball as it moves through the air. Speed. We can calculate the average speed of something moving if we know the distance it moves and the time it takes. Average speed is equals to distance upon time. In symbols, this is written as V is equals to d upon t, where V is the average speed and d is the distance traveled in time. The photograph shows Ethiopia's Kenisia Bekele posing next to the scoreboard after breaking the world record in men's 10,000 meter race. The time on the clock in the photograph enables us to work out his average speed. If the object is moving at a constant speed, this equation will give us its speed during the time taken. If its speed is changing, then the equation gives us its average speed. Average speed is calculated over a period of time. If you look at the speedometer in a car, it doesn't tell you the car's average speed. Rather, it tells you its speed at the instant when you look at it. This is the car's instantaneous speed. Units. In the System International de Units, the SI system, distance is measured in meters, m, and time in seconds, s. Therefore, speed is in meters per second. This is written as meter per second minus 1 or as meter per second. Here s minus 1 is the same as 1 upon s or per second, where there are many other units used for speed. The choice unit depends on the situation. You would probably give the speed of a snail in different units from the speed of a racing car. Table 1.1 includes some alternative units of speed. Note that many calculations it is necessary to work in SI units, ms, meter per second minus 1. Determining speed. You can find the speed of something moving by measuring the time it takes to travel between two fixed points. For example, some motorways have emergency telephones over 2000 meters. Using a stopwatch, you can time a car over this distance. Note that this can only tell you car's average speed between the 2 points. You cannot tell whether it was increasing in its speed, slowing down, or moving at a constant speed. Distance and displacement, scalar and vector. In physics, we are often concerned with the distance moved by an object in a particular direction. This is called displacement. Figure 1.8 illustrates the difference between distance and displacement. It shows the route followed by walkers as they went from town A to town C. Their winding route took them through town B, so that they covered a total distance of 15 kilometers. However, their displacement was much less than this. Their finishing position was just 10 kilometers from where they started. To give a complete statement of their displacement, we need to give both distance and direction. Displacement 10 kilometers 30 degrees east of north. Displacement is an example of a vector quantity. A vector quantity has both magnitude, size, and direction, distance. On the other hand, is a scalar quantity. Scalar quantities have magnitudes only. Figure 1.8. If you go on a long walk, the distance you travel will be greater than your displacement. In this example, the walker travels a distance of 15 kilometers, but their displacement is only 10 kilometers. Because this is the distance from the start to the finish of their walk. Speed and velocity. It is often important to know both the speed of an object and the direction in which it is moving. Speed and direction are combined in another quantity called velocity. The velocity of an object can be thought of as its speed in a particular direction. So, like displacement, velocity is a vector quantity. Speed is the corresponding scalar quantity because it does not have a direction. So, to give the velocity of something, we have to state the direction in which it is moving. For example, an aircraft flies with a velocity of 300 meters per second due north. Since velocity is a vector quantity, it is defined in terms of displacement. Velocity is equals to change in displacement upon time taken. Alternatively, we can say that velocity is the rate of change of an object's displacement. From now on, you need to be clear about distinction between velocity and speed and between displacement and distance. Table 1.2 shows the standard symbols and units of these quantities. Speed and velocity calculations. We can write the equation of velocity in symbols. V is equals to S upon T. V is equals to delta S upon delta T. The word equation for velocity is change in displacement upon time taken. Note that we are using delta S to mean change in displacements. The symbol delta, Greek letter delta, means change in. It does not represent a quantity in the way that S does. It is simply a convenient way of representing a change in the quantity. Another way to write delta S would be S2 minus S1, but this is more time consuming and less clear. The equation of velocity v is equals to delta s upon delta t can be rearranged as follows depending on which quantity we want to determine. Change in displacement is equals to v into delta t. Change in time is equals to delta s upon v. Note that each of these equations is balanced in terms of units. For example, consider the equation for displacement. The units on the right hand side are meter per second into second, which simplifies to meter, the correct unit for displacement. Note also that we can of course use the same equations to find speed and distance, that is v is equals to d upon t. Distance is equals to v into t. Time is equals to d upon v. Making the most of units. In the worked example 1 and worked example 2, units have been omitted in intermediate steps in calculations. However, at times it can be helpful to include units as this can be a way of checking that you have used the correct equation. For example, that you have not divided one quantity by another when you should have multiplied them. The units of an equation must be balanced just as numerical values on each side of the equation must be equal. If you take care if you take care with units, you should be able to carry out calculations in non-SI units, such as kilometer per hour, without having to convert to meter and seconds. For example, how far does a spacecraft travel at 40,000 km per hour travel in one day? Since there are 24 hours in one day, we have distance travel is equals to 40,000 km per hour into 24 hours. 960,000 kilometers is the distance traveled. Displacement time graphs. We can represent the changing positions of a moving object by drawing a displacement time graph. The gradient slope of the graph is equal to its velocity. The steeper the slope, the greater the velocity. A graph like this can also tell us if an object is moving forward or backward. If the gradient is negative, the object velocity is negative. It is moving backwards. Deducing velocity from displacement time graph, a toy car moves along a straight track. It is displacement at different times is shown in table 1.3. The data can be used to draw a displacement time graph from which we can deduce the car's velocity. It is useful to look at the data first to see the pattern of the car's movement. In this case, the displacement increases steadily at first, but after 3.0 seconds it becomes constant. In other words, initially the car is moving at a steady velocity, but then it stops. Now we can plot the displacement time graph. We want to work out the velocity of the car over the first 3 seconds. We can do this by working out the gradient of the graph, because velocity is equals to gradient of displacement time graph. We draw a right angle triangle as shown to find the car's velocity. We divide the change in displacement by change in time. These are given by the two sides of triangle labeled delta S and delta T. Velocity is equal to change in displacement upon time. If you are used to finding the gradient of a graph, you may be able to reduce the number of steps in this calculation. Combining displacements. The walkers shown in figure 1.12 are crossing difficult grounds that navigate from one prominent point to the next. Traveling in a series of straight lines from the map, they can work out distance that they have traveled and their displacement from their starting point. Distance traveled is 25 kilometers. Lay thread along route on map, measure thread against map scale. Displacement is 15 kilometers northeast. Join starting and finishing points with a straight line, measuring line against scale. A map is a scale drawing. You can find your displacement by measuring the map. But how can you calculate your displacement? You need to use ideas from geometry and trigonometry. Worked example 3 and 4 show how. This process of adding two displacements together or two or more of any type vectors is known as vector addition. When two or more vectors are added together, their combined effect is known as the resultant of the vectors. Combining velocities. Velocity is a vector quantity, and so two velocities can be combined by vector addition, in the same way that we have seen for two or more displacements. Imagine that you are attempting to swim across a river. You want to swim directly across to the opposite bank, but the current moves you sideways at the same time as you are swimming forward. The outcome is that you will end up on the opposite bank, but downstream of your intended landing point. In effect, you have two velocities. the velocity due to your swimming, which is directed straight across the river, the velocity due to the current, which is directed downstream at right angle to your swimming velocity. These combine to give a resultant or net velocity, which will be diagonally downstream. In order to swim directly across the river, you would have to aim upstream, then your resultant velocity would be directly across the river. Chapter end.